And with that, our presentation today features a project from the University of Wisconsin, and I'm pleased to welcome our presenter, Kelvin Santiago.
Okay, thank you, Jacob, and welcome everyone. Hopefully everyone can hear me. And let's just begin by talking about flashing yellow arrows. So what I'm going to be doing today is kind of discussing an approach to collect data that would allow us to understand how vehicles and pedestrians interact in the presence of a flashing yellow arrow. Specifically, the type of data that we can collect with the procedure shown, what it will allow us to do, or what we hope it would allow us to do, is to do sort of a virtual before and after study in which we can tell if treatments such as a flashing yellow arrow can improve the safety of a pedestrian for right turns, for left turns, or for anything else for that matter. So with that in mind, let's begin and just talk a little bit about the outline. And the reason I'm starting with this is because I want to make something clear. I'm going to be spending a significant amount of time on background information because it's important to understand the project goals. So when I talk about background, some of the stuff that I'm going to be showing is something that was done earlier for SaferSim. Some of the stuff was later on a kind of an independent project from SaferSim, and now what we did as part of a SaferSim project. So this has been a running process. After that, we'll talk about the goals, specifically what were the goals of the project because of COVID and that kind of stuff. And I want to tell you about how we can collect the necessary data using a field data collection method as well as a driving simulator method. So with that in mind, let's go ahead and understand what we're talking about. So this is a right turning vehicle, specifically approaching a signalized intersection that has a right turn flashing yellow arrow. So let's play this video. And what's happening here is that there's a pedestrian coming. The vehicle slows down. Once the vehicle slows down, it is going to yield to that pedestrian, and then it's going to continue its path. Now, the theory behind this, or when a flashing yellow arrow is present, technically the goal is to improve the safety of that vehicle-pedestrian interaction. If we go back on the video a little bit and we play it again, what will happen in here is that if this vehicle was not really concerned too much for safety, it will go right now, just cut in front of the pedestrian, that kind of stuff. So there is a sense of respect by the vehicle to the pedestrian. How much respect is paid to the pedestrian? That can be quantified mathematically. So if we were to compare the behavior observed on two similar sites, one with our flashing yellow arrow, one without a flashing yellow arrow, if we mathematically compare the amount of respect, and I'm putting that on air quotes, then we will say, oh, the flashing yellow arrow is effective at improving safety or not effective. So it's a way of understanding safety without having to think about crashes, because just because there's not a crash doesn't mean that there's an intersection is safe. So this is another example. No flashing yellow arrow in here, right turn. So there's going to be vehicles that, regardless of what happened, they're going to yield to pedestrians. They're not going to worry too much. They're going to be careful. They're going to go slow down, make sure they're right when they're doing the turn. So the question is there a quantifiable way when we look at a larger population in the way that vehicles and pedestrians interact? Is there a quantifiable difference? So, and this is some sort of a modified approach to how we look at left turns and right turn maneuvers. Typically, everything that has been done, or most of the things that have been done, when we look at how vehicle and pedestrians interact, or even for the fact how vehicles interact with each other, we're looking at gap acceptance models. It's the probability of a vehicle going or not going. Yes, that can be used a little bit of as an indicator of safety, but I'm going to argue that we can do better than that, and we can actually quantify those interactions. The challenge is that getting that type of data, it's very difficult. It is easier to compute. It is easier to compute the probability of a gap being accepted because we've been doing that forever. But quantifying that interaction is a little bit more of a challenge, even as large data sets become available through image processing, that kind of stuff. It's still a challenge to do. We really don't have tools that make that kind of process easier. And what we're going to do as part of this project is try to contribute a little bit to make that process a little bit easier so that we can do evaluations of flashing yellow arrows, or for that matter, any other type of similar technology. And the other thing is, like, we want to use or create tools that rely on commercially available equipment. A lot of the stuff that you see for vehicle-pedestrian interaction modeling has been collected using research-driven tools, tools developed for research, but they don't interact with existing things that are installed at signalized intersections out there, which means that you have to instrument an intersection, and that makes it a little bit more challenging to deploy in the field. Anyways, so with this in mind, what I'm going to do is talk a little bit about the process that we follow in here. Now, imagine that you have this intersection. How can we quantify the interaction of vehicles and pedestrians? Well, what we are going to do is identify certain points on the intersection. If you had a vehicle that was particularly going this way and approaching this thing in here, this area, this crosswalk, if there was a pedestrian crossing in this direction, technically, a theoretical conflict point exists right here. Now, the indicator of safety that I propose we looked at is the following. If your pedestrian was in here when the vehicle was here, and the vehicle was already going, that's a safe interaction. However, if the vehicle was here at the conflict point, and the pedestrian was here, and the vehicle, if the pedestrian was here, and the vehicle was here, and just, went fast, the difference in time between the vehicle arriving in here and the pedestrian crossing in here, if that time gets small, that's a bad indicator of safety. That means no respect for the pedestrian. So that's kind of the interaction that we want to quantify, which for those of you who might be familiar with surrogate safety measures sounds like a PET, post-encroachment time value. Okay, except that we're not only monitoring the post-encroachment time value. What I propose that we do is that we model what is the behavior that this vehicle exhibits as a function of the position of the pedestrian within the crosswalk. If they have completed 10% of the turn, if they have completed 10% of the crossing versus if they have completed 50 or 100% of the crossing. Okay. If we can model that, then we can use that model to understand the safety of the interactions themselves. So here's kind of what we did before this project, is understand these interactions. And we sat down with a camera, collected data, and we look at, okay, this vehicle in here and this pedestrian in here, we monitor their positions over time. Using that data, we created a model. Now, we were very picky in how we developed that model, or how we demonstrated the development of that model. And that is, we look at one-to-one interactions. We didn't look at basically clusters of pedestrians. We didn't look at situations in which pedestrians were crossing, opposing directions. We only look at either single pedestrians or pedestrians that were walking together. Those are the only situations in which we look at are the ones that we shown here. Anyways, we collected timestamp data, we collected position data, merge it into a data set, and effectively what happens is we came up with a model, this model that you see in here. Now, how do we come up with that model? Well, we looked at a site, or we look at multiple sites, and we actually developed a baseline behavior. And by baseline, I mean, okay, these right-turning vehicles in here, how do they behave when there are no obstructions, when there are no pedestrians present? How do they complete that right turn? What is the average time that it takes? Okay. And by the way, this is for right turns that are unobstructed, but not that are green. Okay, so I just want to make that clear. So kind of homogeneous right turn behaviors in here. So you come up with a baseline, you say, okay, this is how we expect these right turning vehicles to behave. This is the type of behavior that we see. That's the time that it takes to complete the maneuver. Then the indicator of safety that we wanted to model was how much a driver deviates from that expected behavior. That is what I talked about earlier about the sign of respect. How much respect does the driver basically has for the presence of a pedestrian? Are they going to delay their maneuver significantly? That is a good indicator that they understand that there's a pedestrian. I'm going to behave as I should behave. If they actually see a pedestrian and they speed up and behave more aggressively, that's an indicator that the driver probably doesn't have a lot of respect for the presence of a pedestrian. You actually see that at intersections all the time. Some drivers like to play chicken with pedestrians. It happens, it's a scary thing, but it happens a lot. So using that information, remember, we got the deviation from expected behavior. That's what we're modeling, okay? But just to make it clear, if we wanted to keep things simple, we can model just the time to complete a right turn. And you can see it in here like that, okay? So, and now what do we model it against? Well, we model it against how long the pedestrian has to basically reach the point of conflict on the road. As you can see, if basically the pedestrian, what this model is telling us in here is that if the pedestrian is far away from the conflict point or is approaching the conflict point, drivers tend to recognize that they're entering a potential conflict zone and they delay their maneuver. Versus if the pedestrian is already past this conflict point and the vehicle is already turning, drivers don't care too much. They understand there's no more danger. So we see the expected behaviors out there. Now, when we focus our analysis on basically that actual change, that deviation, that indicator of respect against the position of the pedestrian, basically on the crosswalk, we can come up with a model like this one in here. So this can be explained a little bit with a linear model. Now, what this is showing us in here is that we repeated the same experiment on a circular green and the same experiment on a site with a flashing yellow arrow. Now, this difference between the two, that space between the circular green and the flashing yellow arrow, can be used as an indicator of safety. And I want to be absolutely clear about this. We are not claiming that this represents every flashing yellow arrow out there. We're just proving that it can be modeled. It's very important. I don't want to make any claims in here. I'm just saying that that behavior, that interaction of vehicle pedestrians can be quantified using simple models. And theoretically, if our baseline behavior happens to be this line, in which as the pedestrian is basically away from the conflict point, the driver is going to, in general, slow down in general. Now, if this is the behavior for the baseline, for the circular green, if we were to have a flashing yellow arrow model that looks like this, that means that the flashing yellow arrow itself will actually make pedestrians less safe. If we have a model like this, that means that the flashing yellow arrow is super good at improving the safety of the interactions. The models that we looked a little bit slightly below in here. I'm not claiming anything. I don't want to make that sure. We were just focusing on the feasibility of modeling the data in there. So this is a good indicator of safety. Now, here's a challenge. Collecting this data that we have in here is super difficult. Okay, you need to go and basically look at every single vehicle, manually look at every single vehicle pedestrian interaction in there, monitor the position of the pedestrians, which by the way is a simple part. Monitoring the position of the vehicle is a little bit more challenging. Okay, so because of that, this is where this project comes in. How can we streamline this process? What can we do around here? Well, if we want to rely on field data, and we have sites from which we can collect data, we can use radar systems to actually monitor the position of the vehicle. Because once we have the position of the pedestrians, if we're merging it with the position of the vehicle, the challenge is getting the position of the vehicle. Now, here's where we come in. We can get radar data for signalized intersections, and it's going to look like a mess like the one you see in here. This represents the position of vehicles, over time. In fact, this is just a short, about 300 seconds of data, not even that, just a small amount of data in here. It's like it's making sense of that data. It's like, okay, this point in here, does it represent a through vehicle? This point in here, well, yeah, that's probably a right turning vehicle, or it could be a vehicle from this direction. Who knows? Luckily, there's been techniques that we developed to analyze this data. Not a problem. The challenge is that, well, the good thing, not the challenge, the good thing is that once we have this type of data, we can extract basically a time space diagram for every single vehicle that approaches the intersection. You can see it in here. This is the y coordinate, which means basically this in here. And this is the speed in here, which means that, hey, the vehicle approached, stop, start to move, stop, start to move, and went. Okay. So we can get this data without any problems. The challenge is making sense of, okay, this maneuver, does it actually represent a right turn, a through movement, or a left turn? Flashing yellow arrows, we can use them for right turns or left turns. Well, here's what we did. That becomes a challenge. The data in itself is just a mess. We came up with a basically summary data set. We summarize the data. We look at, hey, this vehicle, where did it start? Where did it end? And a lot of times that can be simple. For example, if you have a signalized intersection that leads an approach on a signalized intersection, and you have a vehicle that started here and went this way, that is clearly a right turn. If you have a vehicle that started here, went this way, that is clearly a left turn. A vehicle started here and ended up this way, that is clearly a through movement. That's not the challenge. The challenge is that radar systems, just like video cameras and everything, don't work always perfect. They have occlusion issues. They get blocked by views. So we want to maximize the amount of data that we collect. So the challenge is when this vehicle, the only information that we have is about here. This vehicle, that's all we have. We have start here and see here. Does this vehicle represent a right turn or a through movement? That's where we added something in here. And we did something, I think, a little bit clever in here. And what we did is, if we have, again, our intersection, if we have vehicles that started here, 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 ended up here, then here, 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 these vehicles are clearly left turns or right turns. So we started with this, we start with this data set, and we say, okay, this in here, even though I cannot manually verify them, I'm going to treat them as ground truth. And remember, for each vehicle, we have the position, the time, the speed, we have information like that. So we feed that into a machine learning model, support vector machine. And what that allows us to do is by dynamically generating the ground truth data, saying, okay, any vehicle that is on the extremes is clearly something. Using that data, we can extract properties from these vehicles at the stop bar and at other points. And using that information, we can help classify these impartial trajectories. And that allows us to maximize the amount of classifications that we can obtain from data, because we want to extract the trajectories of vehicles that make a right turn or left turn in order to model the vehicle-pedestrian interactions. So using that machine learning model, we can demonstrate that is possible. Now, if you run this process through MATLAB, you're going to get this chart, which I'm the one that's going to tell you, ignore it, but it's always good to see 100% here, 100% there. That's not the purpose of this chart. The point is, like, with this, you get a relatively simple support vector machine model that then you can apply to unclassified data. And when you apply that to unclassified data, then you can take every single vehicle trajectory that you have in your data set and assign a movement in here. And now I can go in and say, oh, these are right turn, right turn, right turns. I can extract that data and use it for modeling vehicle-pedestrian interactions. Okay. Now, when we look at the performance of this, and this is why I say, don't look at that previous ROC table. Like, no, the 100%, no, it's just a joke. The reality is that when we put this to the test at a particular intersection, that approach, we end up with, for example, for right turns, this is what we have in here. For right turns, we end up like on average, you get a 1.1 absolute vehicle difference between ground truth data, real ground truth collected by manually analyzing video and analyzing the trajectory data. So peaks like this in here, this is basically a difference over a period of time. This is like, okay, at this time interval, what was the difference between ground truth and classified trajectories? That's what it is in here. This is probably explained by occlusion effects. So data is not perfect, we're not claiming that, but on average for right turns, we observe 1.1 vehicle difference in here. So the model is promising. Anyways, so here's where the next part of the project comes in. It's like, that's great. If we have field data, and we have the equipment at the intersections, we can actually obtain the necessary data to rerun those experiments that I talked in the background section. But now can we do the same thing with the driving simulator experiments? And the challenge with using driving simulators for studying flashing yellow arrows, for anyone that's done this, is that the driving simulators were not designed with the goal of having complex vehicle signalized intersection operations. Okay, so it's always kind of like a hack to get it going to do flashing yellow arrows, which is fine. So we say, okay, if we wanted to streamline this process, what can we contribute in here? What can we do in here? Well, this is where we created a set of effectively tools to streamline the process of creating driving simulation experiments that involve flashing yellow arrows in an environment like Unity, to basically enable VR in the future, enable any type of experiment that involves Unity in here. And I'm going to switch screens in here because I want to show you the collection of tools that were created in here. This is just a mock-up intersection, basically containing like a mock-up experiment in here. It's like my test bed. It changes daily. So what I'm going to do is show you how easy we can just add a signal that operates to Unity. I'm going to switch screens in here to an empty Unity project, and we are posting this prefabs for Unity into GitHub for anyone to use. Okay, so let's say I wanted to build a flashing yellow arrow experiment in here. I'm going to start by basically adding a signalized intersection. I'm going to go with a 4, basically, oops, just testing in here, making sure it works. I'm going to start by bringing into my model a 4-section signal head. I import everything. And again, we're posting this on GitHub for anyone to use. Dropping this in here. Okay, so now I have my 4-section signal head in here. We're making operation of this quite simple. I'm going to play this. In fact, I'm going to run this model as it is right now. I'm going to go in here. I'm going to show that basically the way that this was created, I can make things, I can make any signal. I can change the states. I can make this red. I can make this yellow. I can make anything flash in here. Doesn't have to be anything particular. So we created this collection of prefabs in here, and basically they operate like that. Now, okay, that's a signal head. I'm going to bring basically now I'm going to bring a sensor to basically allow turning of the vehicles. I'm going to bring a sensor in. I'm going to import everything. I'm also going to bring a stop bar control. I'm going to bring that in. And here, bring the stop bar control. I need to bring a virtual control in here. I'll drop this prefabs in here. And I'm going to bring I have a curve maneuver, stop where I'm going to bring a vehicle, just a mock-up vehicle in here, and I'll bring it in here. Okay. So I'm going to bring my vehicles in here. Anyways, so what do? I can have stuff appear in here in Unity. How do we make things turn? How do we make this fast? I'm going to add a curve turn. I'm going to make the vehicle stop in here like that. And then I'm going to bring in a virtual control that I'm going to drag in here. Anyways, so I have this in here, and I can just kind of show this is a stop bar sensor. It'll disappear if we run it, but I'm going to say, okay, you're going to listen for information on this face. So I just link that stop bar sensor to this signal head in here. This curve maneuver, I'm going to make this be, okay, I'm going to make a minus 90-degree turn. That means a left turn. And the turn radius is going to be 50. If I actually run this simulation in here, and then I'm going to make this signal in here, I'm going to go in here and say, hey, I want to make this movement allowed. No, I want to make it stop. If I make this go, now if I look at my vehicle, it stops as it approaches the intersection. Now, if I were controlling this programmatically, I'm just going to make this be a signal state 3 in here to make it yellow. Then I'm going to tell the instruction, hey, you can move. The moment that I hit move, notice that this vehicle actually starts a turn. So we made the process of actually running a flashing yellow arrow in Unity quite simple to do. Just operate however we want. We can illuminate things however we want. There's no hacking of the simulation environment. We're just making it work so that we can run those experiments. It's simple. So in conclusion, basically what we've created in here is just a collection of tools that allows us to run driving simulator experiments that involve flashing yellow arrows faster, as well as collect field data faster, so that we can really go back and obtain the necessary data to do before after evaluations of a flashing yellow arrow impacts on vehicle pedestrian interactions. Anyway, that's it from my end. I know we're about 3 minutes away from the time, so if you have any questions, please let me know.
Thank you, Kelvin. And as he just mentioned, we will open it up for any questions or comments. Really appreciate the presentation and the thorough demonstration too. So as we're waiting for questions or comments, I will thank everyone for hopping in this afternoon. As I mentioned at the beginning, this presentation will be available online on our YouTube channel and website in the next couple of days, and we will share that link with all the registrants. And feel free to share that with any colleagues that may be interested. Kelvin, we may be able to share that GitHub link in that email if that works for you, but we'll be in touch about that.
So I see a question in here. Let me read it for the audio. Are intersection geometrics taken into consideration? Turn radius, crosswalk, setback, etc. So the way that I designed those sensors is that you have the freedom to specify those manually. For example, in that turn, I was able to specify how much do I want that vehicle to turn and what is the radius. And by how much, I mean, what is the end? Every vehicle has a, if you go back to like the thing like surveying class, you have an azimuth. Every vehicle has an azimuth when it's traveling. When the vehicle approaches the turn sensor, it says, hey, I want you to change your azimuth by minus 90 degrees. Think of it like a control tower. Change course to this and change that course on a particular radius. So I can make that match the radius of the intersection. So when you do these experiments on a platform like a typical driving simulation platform, you have to configure the rows and configure the links, and then add the metadata. None of that is just a set of instructions. The world on which the vehicle drives is basically not important to the vehicle to that extent. It's just going to follow a set of instructions, and it makes things a little bit simpler for coding that behavior of the vehicles.
Awesome. Okay. Well, we are just about at time. I'll give it some final moments here for final thoughts. And I will get in the pitch for our next webinar, which will be September 22nd. That will be a Wednesday, so that's different than our usual Tuesdays, but we are working with a professor's class schedule this semester. We will be sending that information out here in the next couple weeks, and we will be sending the recording of this webinar before then. I think that looks like we don't have any other questions then. So with that, we can wrap it up. Kelvin, I appreciate your time, and everyone for attending. Thank you for joining.
Thank you, everyone.